All right, here we are. If you are watching this video, then you should have already watched the introduction video, completed your spiral review homework, morning work, I guess, the Monday section, and then you should have answered the question of the day. If you have not done all of that, then you can stop this video and go back and make sure your spiral review is completed before we check it. Now I'm going to give you the answers. I don't have my fun manipulatives to pull out and explain things to you, but one advantage you do have with this video is that if you don't understand something, you can stop it, go back, watch it again. So I'm not going to take too much time sharing the answers with you because you'll be able to go back and watch again if you don't understand the first time. I hope that will make it so that you're only listening to what you need to, and that you can move on with your day as soon as possible. The first question says, what is the value of the underlined digit? Another word for value that we practice using is magnitude. Value and magnitude both talk about how much power a number has. So a 2 is the underlying digit, and it's in the tens thousands place. So the value or the magnitude, how much power that 2 has in the 10,000s place, is 20,000. Next, we have an 8 underlined in the tens place, and the value or the magnitude of an 8 in the tens place is 80. Next, it says find the difference. Difference is the answer to a subtraction problem, so I'm going to subtract 48,007 minus 9,758. 7 minus 8, you can't do it, so you have to borrow. The 7 looks at the 0, but the 0 doesn't have anything to give. So this 0 looks at the other 0, and that 0 doesn't have anything to give. So this 0 is going to look at the 8, and the 8 has something we can borrow. So the 8 turns into a 7, so that the second 0 can become a 10. Now the first 0 can borrow from the 10, so the 10 becomes a 9, and the first 0 becomes a 10, and now the 7 can borrow from the 10, and so the first 0 that's now a 10 becomes a 9, so that we can have 17 minus 8. 17 minus 8 is 9. 9 minus 5 is 4. 9 minus 7 is 2. 7 minus 9, you can't do it, so you borrow. The 4 becomes a 3, and we can have 17 minus 9. 17 minus 9 is 8, and we have a 3 for 38,249. Next question says find the quotient. We have 5,487 divided by 7 because quotient is the answer to a division problem. All right, if you were here, I'd have you talk with me. I wish that you were here with me, but I guess I'll do it on my own. Here we're seeing how many times 7 goes into 5. 7 doesn't go into 5, so we underline the 5 and the 4. This shows that we're using both of those digits. Now, we're seeing how many times does 7 go into 54. If you didn't know how many times, you should list out your 7s. 7, 14, 21, 28, 35, 42, 49, 56. So this shows that 7 can go into 54 1, 2, 3, 4, 5, 6, 7 times. The 7 goes on top. We write 49 under 54 because 7 times 7 is 49. 54 minus 49 is 5. Bring down the 8. 7 goes into 58 8 times for 56. 58 minus 56 is 2. Bring down the 7. 7 goes into 27 3 times for 21. 27 minus 21 is 6. We don't have any more numbers to bring down, and 7 can't go into 6 any more times, so the 6 is our remainder. The final answer for this question is 783, remainder 6. Every year, Marla collects acorns. If she collects 1,378 acorns each year for 7 years, how many acorns will she have? It might help if you kind of wrote out these numbers to think about it. So she's going to have 7 years, and each year she's going to have 1,378. 1,378. 7 times. You could add all of those 7 times, but we know that repeated addition is the same as multiplication. So I'm going to go ahead and multiply 1,378 acorns times 7 years. That's 1,378. 1,378 7 times. Let's do it. 7 times 8 is what we do first. 7 times 8, 7, 14, 21, 28, 35, 42, 49, 56. You write the 6 at the bottom, carry the 5. 7 times 7 is 49, plus your 5 is 54. 7 times 3, 7, 14, 21, plus your 5 is 26. Write the 6 at the bottom, carry the 2. 7 times 1 is 7, plus 2 is 9. So we got 9,378, and a good label for this is acorns. Make sure you have a good label. This is a reasonable answer for this question because 1,378 is about 1,300. And so we know that our answer is going to be bigger than 7,000. And so this is a reasonable answer. All right, let's move on. Complete the pattern. When we see a pattern, we have to think about, are the numbers getting bigger or are they getting smaller? To get from 17 to 15, the number gets smaller. We have two operations that take a number and make it smaller. That's division and subtraction. Let's think about division first. Is there a number I can divide 17 by to give me 15? Maybe, but I'm not really thinking of it right now. Let's move on to subtraction. To get from 17 to 15, I can subtract 2. So there's a good chance that could work, but we always check to make sure it works for all of the steps. Next, we see if we can subtract 2 to get from 15 to 13. We can. And from 13 to 11, minus 2 also works. So as we continue our pattern, 11 minus 2 is 9. 9 minus 2 is 7. That is what our completed pattern looks like. You should have all of this written down. Make sure you have the correct answers. And I hope that you caught a mistake. All right, let's keep going. Compare fractions using greater than, less than, or equal to. Here we have 7/8 and 3/4. I'm going to draw two rectangles that are of equal size right next to each other so that we can compare them more easily. Let's start with 7/8. 7/8 has a denominator of 8. The denominator tells us how many parts in a whole and therefore what size they are. So I'm going to split my first rectangle into 8 parts by splitting it in half, splitting those halves in half, and splitting each of those pieces in half. Now I have 8 pieces, and I'm going to shade in 7 of them because our numerator is 7. Next I have 3/4. The denominator tells us we need this split into 4 parts, and the numerator tells us we need 3 of them shaded in. Something I noticed right away is that both of these fractions have one piece missing, but the first fraction has 1/8 missing, and the second fraction has 1/4 missing. We're comparing the part that's shaded in, and so the one that has less missing has more shaded in. So 7/8 is greater than 3/4 because it has a smaller piece missing. Now let's compare 1/2 to 2/5. I'm going to do the same thing where I draw two rectangles as close to the same size and shape as possible so that I can compare more easily. 1/2 split into 2 parts with 1 shaded in. 2/5 split into 5 parts with 2 shaded in. There we go. There's my 5 parts. And here are my 2 shaded in. I can see that 1/2 goes up higher, and so there's more shaded in 1/2. 1/2 is greater than 2/5. Next, it says solve 4/5 plus 3/5. I'm going to draw it out since I guess I don't have my little bars to show you what it would look like if we were using our fraction bars. But we're talking about fifths. So all of my wholes need to be broken up into 5 parts. Here they are. Here's some fifths. Here are some more fifths. First, I have 4/5. 1, 2, 3, 4/5. And then I add 3 more fifths to that. 1, 2, 3. 4/5 plus 3/5 they stay fifths. My denominator is definitely going to stay a 5. And 4 plus 3 is 7 fifths. 7 fifths could also be correctly written as a mixed number for 1 whole and 2 fifths. You can see that because this whole thing is shaded in, and then there are 2 fifths next to it. 1 whole and 2 fifths is equivalent to 7 fifths. Now let's do 7 eighths minus 5 eighths. I'm going to draw a tape diagram. Split it into eighths. Half, half, half again. And then I am going to shade in 7 eighths. And then we essentially take away 5 of them. Get rid of you, get rid of you. 3, 4, and 5. 7 eighths minus 5 eighths. We have to keep the denominator when we add and subtract because these don't turn into a different size. We just took away 5 of them. 7 minus 5 is 2 eighths. Next, this says, are the two problems equivalent? This might remind you of what you were doing in Zern the week before we got out. And this is saying 3 times 3 tenths and 3 times 3 over 10. Are the two problems equivalent? Something I noticed that looks pretty good to me is that both of these have a denominator of 10. If there's no reason, which we haven't learned a reason yet, for the denominator to change in a problem, the denominator is going to stay the same. We're talking about tenths, we're talking about tenths. So the fact that they're the same denominator is good. These are actually equivalent, and I'm going to talk about how. So 3 times 3 tenths, it's like you had 3 little tenths, and these would be out of a hole like this. But the 3 little tenths that I have, if we had 3 tenths 3 times, then we would have 9 tenths. So 3 times 3 tenths, or 3 tenths 3 times, is 9 tenths. And then we can look at the second one. 3 times 3 is 9, and if you left it over 10, that would also be 9 tenths. All right, and down here it says, what multiplication problem does this model represent? I'm going to start by labeling one of my little circles here. So there are 5 pieces, so my denominator is 5, and 2 of them are shaded in, so this is 2 fifths. All of them are going to be 2 fifths. 2 fifths, 2 fifths, 2 fifths. So you could write this as 2 fifths plus 2 fifths plus 2 fifths, but our question is saying what multiplication problem. So we're definitely going to have 2 fifths in there, and it's going to be 2 fifths 3 times. So we can write this as 2 fifths times 3. We know that repeated addition is the same as multiplication, so 2 fifths plus 2 fifths plus 2 fifths is 3 2 fifths, or 2 fifths times 3. All right. This Monday section of your spiral review is something that you're going to need to bring back to school with you, so make sure that you have all of the answers correct, and if you need to go back and review one of the questions, you can absolutely pause and review it. Keep track of this paper, and I hope the rest of your work goes well.